I like example 1. I like example 1. Example 1 is a nice question. Well, example 1 and the bow and arrow question, because to me these are really the same physics. In both of them, you're pulling on something that's stretchy or elastic. You're storing energy. And what kind of energy are you turning it into when you let go of it? Kinetic. Okay? So it says this: a slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. How much PE is stored in the slingshot? A lot of students do something like this. Don't write this down, don't write this down, don't write this down. They go, oh, potential energy is mgh. That's the energy that you gain by lifting something against gravity. Are we lifting something here against gravity? So don't use that one. There's a more generic definition of potential energy, because energy is the ability to do work. How do I find work? Yes. Did they give me a force? Did they give me a distance? That's your hint. It's going to be 70 times 0.9. 63, double check me, but I think I'm right. Good to see Brian getting his calculator finally. Cole's even thinking about it as well. Good. 63 joules? And you could actually do this if you wanted to with a slingshot. If you measured the distance with a ruler and you measured the force with a force gauge, a fishing scale, a spring scale would probably work. You could then make an estimate as to how fast the slingshot should fire a projectile. If there is a 35-gram mass in the pouch, how fast will it leave the slingshot? I have to make an assumption. The first assumption is I have to assume that all of the PE turns into KE. David, what's this question you wanted me to find?
How fast?
Do you have the kinetic energy equation in front of you somewhere? You have your yellow sheet out? Or if you know the kinetic energy equation in your head, can you get the V by itself? Because that's how fast. Did I say yellow sheet? You guys have a green sheet, right? My Physics 12 said a yellow sheet. How would I get the V by itself? Oh, he's looking. Chloe, how would I get the V by itself? I'll come back to you, David. You're still hunting.
How would you get the V by itself?
Yeah.
You would divide by M.
What's going to drop down like a domino staying where it is?
By K.
Yep. And divide by M?
Times by 2.
Yep.
And then put in the square root.
Good. And again, I think I said to you, you can times by 2, or if you want to, you can divide by 0.5 if you like decimals better. Decimals inside of fractions to me are bad math manners. I'm not wild about it. So it's going to be 63 divided by 35? Why is 35 wrong? Grams. We don't do physics with grams. 35 grams is 0.35, 0.035, 0.0035, 0.000035, 0.035. Just work out evenly? No. Trying a new calculator. I don't know if I showed it to you last class already or not.
You did.
I did? So, continue with the current version. Problem is every time I open it, I have to muck around with the settings. I need to figure out how to do a save as. Go away. Go away. Go away. Go away. Get out of here. YouTube. And now I can see all the buttons. I think this one actually does a little indentation-y thingy for square root. Okay, let's go like this. Clear, clear, clear. Shift, square root. Yeah, it does. So I can actually go 2 times 63 divided by 0.035 without having to do it first and then go square root answer button. Okay. Oh, is it 60 even? Yes? Wow. You could have nice numbers. And that seems about right, ballpark. I've seen slingshots. In fact, I shot slingshots when I was a kid. 60 meters per second. about a little more than half of the football field in 1 second. That's about how fast the rocks went. Tarzan weighs 82 kilograms. He can run at 8 meters per second. He runs along the ground and he grabs a vine, swinging into the air. Okay. David, now coming back to you. What does this want me to find? Height. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? This is a job for conservation of energy. We used conservation of energy in the previous one, but we didn't bring out the actual equation because it wasn't gravitational potential. It was just stored energy that turned into kinetic. I wrote here DULP. So here's what we're kind of getting at. Here's Tarzan. Oh, that's terrible. Let's give him a better foot. Sprinting. And he's going to grab a vine. And he's going to swing like that. Is that okay, Maggie? So, yeah. Is there going to be a change in height? Yeah. Is there a change in speed? Yeah. Is there a yucky curvy path? This is really a job for conservation of energy. So let's go with this then. K E initial plus P E initial equals K E final plus P E final. Are any of these 0? Let's look at kinetic. Is there ever a moment in time when he comes to a stop? Yes, good, David. There is a moment in time where he comes to a stop. Where does Tarzan come to a stop for a split second? At the top. Is that initial or final? Final? Oh, sorry, kinetic final. Give me 1 second. Let me pause the video. What did we say was 0? Kinetic final? You agree with me, David? Now, let's look at the potential energies. Where is potential energy 0? When you're on the ground. Are we starting on the ground? Are we? Are we starting on the ground? Now here's the nice thing. Technically we're not, because Tarzan is grabbing the vine, I'm going to imagine from around face high, maybe a little bit above his face, and that's not on the ground. But because work and energy is a scalar, we can have 0 be wherever we want. And so, although we're technically not starting on the ground, I'm going to let 0 be that line right there, which means which potential energy is going to cancel? Initial or final? PEI is not a real province, right? It's not a premier, they're a mayor. One of these days, someone from Prince Edward Island is going to watch these videos and I'll be getting angry letters, right? But it's a dumb way to remember. David, what was the equation for kinetic energy? See how I came full circle back? What's the equation for kinetic energy? Yeah, what's the equation for that? You got your formula sheet, though? Oh, no! Okay. Help them out, folks. What's the equation for kinetic energy? A half m, and since it's initial, I'll put the v initial squared equals. Normally I try and keep my equal sign lined up, but since so much stuff canceled, I'll put the equal sign right there. What's the equation for potential energy, folks? David, what does this question want me to find? That bad boy. Oh, David, is there an m in this term? Is there an m in this term? Is there an m in everything? What does that mean? Here's what it really means. If Tarzan, weighing 82, runs at 8 meters per second and swings to a certain height, and Tantor the elephant runs at 8 meters per second and swings to a certain height, as long as the vine doesn't break, they'll both go to the same height. Now, probably the vine would break, and I don't know if an elephant could swing on a vine, but indulge me in the hypothetical. You're right. M cancels. How would I get the H by itself, David, my friend? Absolutely. So, let's see. I'm going to write the h right here if that's okay. I have a vi squared. Yes? What did you say I'm going to do with the g? Okay. Now, if you then look up, everybody look up, all over YouTube. If you did this, I'm okay with that, but is that 1 on the top going to make a difference? So usually what I do here to make it look prettier is I just tuck the 2 down there. That is a 1/2. I just didn't write the 1. That looks prettier. So it's going to be vi squared over 2g. It's going to be 8 squared all over 2 times 9.8. 8 squared is 64, divided by 2 is 32, divided by 9.8. It's going to be a little more than 3.2. Is it 3.3, 3.4? 3.26? Is the 6 rounded off properly? What comes after the 6? So is the 6 rounded off properly? Yes? Is it 3.26 or 3.27, folks? 7. Yes? So 3.27. Units, David, my friend, height. Meters. Boy, without that sheet, you'll do better. Okay. Slap shots are terrific examples of energy transformations. And I'll show you a great Smarter Everyday video, but I'm going to show it towards the end of class because it's a long one and I want to get through this. Roller coasters, roller coasters, roller coasters. How many more am I doing here? Oh, we're doing Rube Gold. Oh, yeah, good. Let's do a roller coaster. Example 3. Roller coaster below has a mass of 255 kilograms. Let's suppose it just barely makes it over the first hill at A. In other words, let's assume that VI is 0 or close enough to 0 that it's negligible. How fast are we going at B? Joel, look at this picture. Is there a change in height? Yeah. Is there going to be a change in speed? Is there yucky curvy path? That's a job for conservation of energy, a scalar approach. We're going to let right here be initial. We'll let right here be final. What's the conservation of energy equation from your formula sheet? What's the law of conservation of energy? Good. Which ones are zeros? What? Kinetic initial, starting at rest. In real life, by the way, you don't come over that top hill quite at 0. You've got a couple of meters per second, and if you go to Playland next year, if you take Physics 12, we'll include that. We would not have a 0, but close. Anything else 0? You make it cold, those bunks are getting longer and longer every time I look back there. Sorry, what's 0? There is one more thing that's 0. Oh, we're on the ground? Well, that's nice. Joel, this question just got way cleaner. Joel, what's the equation for gravitational potential energy? Because that's really what this is. This is the energy due to height. You are correct. And initial, it'll be mgh initial, and that equals, what's the equation for kinetic energy? And since this is final, you mind if I put the F there? Joel, have you gone on a roller coaster before? You have? Before you got on the roller coaster, they made you step on a scale and they took your mass, right? No? They didn't make sure to balance everybody out. They didn't put heavy people with light people. They didn't say that kids couldn't ride. Do you know why? Is there an M there?
Yeah.
Is there an M there?
Yeah.
Is there an M in everything?
Yeah.
What happens to the masses?
Balance.
They don't just balance. There's an M in everything. You know what happens to the masses, folks? David. You told me a little while ago. Oh, he was zoning out. Help him out, folks. What happens to the masses? They cancel. This is why little kids and grown up. This is why, by the way, an empty car will make it through the roller coaster run. You've seen them when they're warming up the track or after the track is closed, or once in a while if there's a glitch and they want to just do a test run, they can send an empty car through. They don't have to put sandbags in there or anything like that. Joel, what am I trying to find?
How fast?
Which variable here? Is it G? Is that how fast?
No.
Is it H? Is that how fast?
Yeah.
H stands for how fast?
No.
Is it V?
Yeah.
Oh, because what has V stood for all year long? Speed or velocity, but we're in Scalarville, so speed. Yes? Okay, so I'm going to get this by itself. How? What's the 1 doing to the V? It's multiplying, so technically I would divide by 1, but is that going to make a difference at all, dividing by... So that's why I always ignore the 1. This 2, it's on the bottom. Yes?
Yeah.
So that means it's dividing. How will I move this 2 over? What's the opposite of dividing by 2? On this side, it'll be multiplying. So if I hear you correctly, and I think I do, you're telling me there's going to be a 2. I think the G and the H initial just drop down like a domino. Yes, 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 yes. Now that would give me, don't write this down, Joel, just look up. That would give me V final squared. How do you get rid of a squared? Okay. And if you don't mind, I'm going to put the V on this side. There. Do you need to memorize that equation, or can you derive it? In theory, we can derive it. You might have to memorize it, but I would encourage you, get comfortable with the formula manipulation. It so cuts down on your memorization. Let's keep going, Joel, you and I. It's going to be 2. G is 9.8. What's the initial height? I've scrolled down. 18?
Yeah.
Really? I thought I made a higher coaster than that. Oh, no, I didn't. Mixing this up. What do you get? Will this work out evenly? Oh, this might actually work out nice. 2 times 9.8 times 18 square root answer button. Oops, that didn't work. Square root answer button. Answer button. Not liking this calculator. I may have to... Oh, wow. That's an interesting way to say the answer. Come on. Fraction to decimal. You get 18.8? Is that right? Yeah, I'm going to ditch this calculator. It's a little clunky. Let's go back to my old one. 18.8. Joel, did you get that as well? Do me a favor. Let's convert that to kilometers per hour. How do you go to kilometers per hour? Is it times by 3.6 or divide? Which one is it? Times or divide? Is it times? Can you multiply that by 3.6? How many kilometers per hour is it? Is that fast? It's not bad. For a roller coaster, honestly, Joel, as someone who's been on a lot of coasters, it's more than meh, but it's not... It's somewhere in the middle. Okay? I've been on those ones. I've been on coasters where you're going faster than 100 kilometers per hour. That gets my attention. Okay? How many of you been on the one at West Edmonton Mall? Have you been on that one? That one I like because there's one loop, there's one section where I actually start to get tunnel vision. I get a little bit of gray out and I start to lose peripheral vision. Oh, that's good stuff. It means you're really pushing the G's. No? Okay. What if instead of hill A being the first hill, what if it was the second hill and we came over it at 22 meters per second? Now how fast are we going to be going? Emily, is there a change in height?
Yeah.
Is there a change in speed?
Yeah.
Is there a yucky curvy path?
Yeah.
I'd use conservation of energy. So it's going to look like this. I think Joel, when he read it to me, I think on the formula sheet I did the PE's first. As long as you have initial plus initial equals final plus final. And apparently I flip-flop between the orders. Are any of these 0? Is our initial kinetic 0 this time? Yeah. Sure would have been nice because it made the math nicer. In fact, the only thing that's 0 this time is Prince of Rhode Island gets to stick around. PEI is not 0. Okay. Kinetic energy is a half m v initial squared plus m g h initial. That equals a half m v final squared. Are you a roller coaster fan, Emily, or not? You're not? Have you been on one before?
Yeah.
When you went on it, did you have to step on a scale?
No.
You know why? What cancels out?
The mass.
Is there an M in everything here? Now, I should point out I'm fibbing a tiny bit. In real life, in the real world, we would have, don't write this down, some energy lost to heat. And is there an M sitting in that little thing right there that you can see? So does the M really cancel? No. But if we grease the roller coaster down as much as possible to get this as close to zero as possible, then although the M technically, Christy, doesn't cancel, it becomes negligible, which is why an empty car or a full car all work, why little kids and grown-ups can go on the same ride. So I should hedge my bets and say, okay, fine, technically the mass doesn't cancel from the heat, but you grease it down. Not generating much heat. Roller coasters are pretty efficient. Again, you may have noticed, typically at the end of a roller coaster, they have to use brakes to slow you down. It's not like you've used up all your energy. You still got plenty of kinetic energy left. Tristan, yeah? Okay. What am I trying to get by itself? Okay. M cancels. And I'm going to show you one more trick. What am I trying to get by itself? What do I have right here? What do I have right here? Do I have a 1/2 there? No, but still, here's the trick I'm going to do. I'm going to multiply everything by 2. I'm going to put a 2 there, a 2 there, and a 2 there. Why did I do that? Cole, what's 2 times 1/2? Not 0. Which means I can just ignore that. What's 2 times 1/2 again? Now here, a 2 sticks around, but I've made this equation much prettier. In fact, now it says this, VI squared plus 2G H initial equals VF squared. Put your pencils down, look up. A long time ago, Maggie, in October, I promised you that I would show you where the following equation came from, where VF squared equals VI squared plus 2AD came from. That's where it comes from. Because isn't G an acceleration in meters per second squared? And isn't that a height in meters? Back then I said to you it was yucky and it was a long derivation. I know that it pops naturally out in one line from conservation of energy. That's where that equation VF squared equals VI squared plus 2AD came from. So I have kept my promise. Shut up. Let's keep going. What am I trying to get by itself, M? How to get the V final by itself? Boom. Massive square root. Yeah. Deal with it. It's doable. It's plug and chug time. V final is going to be 22 squared plus 2, 9.8, 18, square root of all that. (22) squared plus 2 times 9.8 times 18. Wow, that's, square root of that. It's going, that's a great coaster. Faster than sound. You get 28.9? Is that a good coaster? Let's multiply that by 3.6. Oh yeah, now we're going over 100. We're doing freeway speed. I'm in. That's a pretty good coaster. There are coasters that go faster. Nuh-uh. Uh-huh.
I really want to play land.
Uh-huh.
I'll kill myself.
You really won't, but that's okay. And by the way, if you're taking Physics 12 next year, you can still come on the amusement park ride. We do it in groups of 4, and you always need a timer on the ground to time the different sections. And so if you don't want to go on the ride, for once in your life, you'll be popular. That came out wrong. That came out totally. But you know what I mean.
That's just. I won't do this.
You meant that as a threat. I'm sorry. I misunderstood that. Boy, people on YouTube are just, wow, what a weird class. This is going on YouTube. Little physics 12 here. Although maybe I'll keep this in physics 11 after all. Jacqueline, what's C asking me to find? Okay, now we can be a bit more accurate. So supposing we had our radar gun at the bottom, and instead of 28.9, I do have a radar gun, we do bring it to Playland. Instead of 28.9, we clock the roller coaster at 25. That means some energy has vanished. Well, no, it hasn't. It got transferred into heat. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? It's a job for conservation of energy. But now we're going to add one more term, Jacqueline. We're going to say, I guess there is some heat involved here. We still have PE final is 0 because we're ending up on the ground. What am I trying to find, Jacqueline? I'm trying to get the heat by itself. So I guess I'm going to move this over. How would I move the KE final over? What's it doing to the heat? Adding, subtracting, multiplying, or dividing? Adding. So how do I move it over? Loud and proud. Yeah, this is a weird one because I give this question in Physics 12 all the time, and all the time I have kids for some reason divide by KE final. I don't know why, because it's pretty clear. There's two. It's plussing. I don't know why, but they do this all the time. And so, Sierra, once I figure out why, I'll try and prevent it. But for now, I'm just going to say, don't do that. So, an equation for heat, Jacqueline, you're telling me the KE initial would drop down like a domino, and the PE initial would drop down like a domino, and it would be a minus KE final. And do you mind? I'm going to put the heat right there. David, what was the equation for kinetic energy? Yeah, I'm coming back. Oh, good. He's looking now. Jacqueline, what was the equation for gravitational potential energy? David, what was the equation for final kinetic energy? A half m squared. Jacqueline, is there an m right here in this term? Is there an m in this term? Is there an m in this term? Is there an m in heat? So does the mass cancel this time? Did I give us a mass at the very beginning of the question? I hope in part A or in the diagram? I did? What is the mass? Okay, so we can plug and chug now. And this is why I said a few minutes ago, Emily, I fibbed a little bit. In real life, if there is heat, the masses don't quite cancel. But we grease this down to get this as close to 0 as possible so that it's negligible. Right, Cole? Right. I'll use red now for heat. 0.5. What was the mass, Jacqueline? 255? What was V initial? It was, you have to look on the previous page. In part B. 22 squared. Plus 255 times 9.8. Initial height was 18, right, Joel? I think you said? And then minus 0.5, 255. Final speed was 25 squared. And you can see if you look really closely, Hannah, what we're really saying is, here's the energy you started with. Here's the energy you finished with. Some went missing into heat. That's why we're minusing. You could probably type that in one fell swoop in your calculator. I'm going to. One line. A half times 255 times 22 squared plus 255, one more, times 9.8 times 18. Take away a half times 255 times 25 squared. I typed this wrong. You don't get a negative, do you? Where did I make my mistake? 20. Wow. Sheesh. The very first line. This was somehow saying that we had gained energy, which would have won me a Nobel Prize if I was right. Would have been great. Do you get 27,000 and 27,000 joules of heat? Is that okay, Bri? So we can do a lot with this. We can predict how much energy we're losing to heat, and we can then engineer ways, Tristan, to try and lose less energy so that mass becomes less relevant, so that we have a wider safety margin. Usually the solution is grease things down like crazy, because heat typically comes from friction. Example 4. A cart and rider start from rest on a 20-meter high ramp. At the bottom, the car is traveling 15 meters per second. Cole, what's this question want me to find? Sorry? Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? No. But is it talking about heat? This is a job for conservation of energy. And I'm going to use the same equation we did earlier. It's going to be kinetic initial, potential initial equals kinetic final plus potential final plus heat. Mr. Duck? What, Mateo? If I know ahead of time that some of these are 0, do I even need to write them? In your homework, feel free. I almost always do in the notes so that when you're studying later on, you know. But, yeah, honestly, I don't when I'm doing these quickly. Speaking of, Cole, which ones of these are 0? Yep. Yep. What am I trying to get by itself? How? So you're telling me, and you're correct, that heat is going to be the initial potential minus the final kinetic? Yeah. Potential was mgh, initial, and a half mv final squared. You might be tempted to cancel out an m, but is there an m in heat? No. Okay. Heat. I've scrolled down. What was the mass? I hope they gave me one. Oh, they did. 75. 9.8. 20. 0.5. 75. 15 squared. How much energy did we lose to heat? You get 62.5? I'll write down 6,260, but I'll keep this on my calculator. Heat is measured in joules because it's energy. Ah! B. Ugh. Hannah, what's B asking me to find? What? Okay. Don't write this down. My first thought would be to say, well, Duick, friction is mu times the normal force. Yes? Hey, what's mu? I don't know. What's... Oh. Did they give me a mu? What did I find in part A? And what's energy defined as? Energy is defined as the ability to do. So another way to think about heat, it's the work done by friction. And Christian, this is going to be your cue. How do I calculate work? Sorry? Can you use the words? Did you say force?
Yeah.
Ooh. What are we trying to find here? Force? Did you say force? Did you just give me a work equation with force in it? And did I just find the work done by friction in part? Because that's another way to think about heat. You see how we're putting everything together? Here's yet another clever way we can do this. So I'm going to argue that this is going to be the work done by friction. Wow, that was kind of cool how it changed halfway through. The work done by friction equals the force of friction times distance. Hannah, how would I get the force of friction by itself? Yep. It's going to be the work done by friction, which is heat, divided by D. Hannah, what was the heat? It was 62.5? Which D? Do you notice the picture gave me 2? Christian, what? Why the 60? Because the force and the distance have to be in the same what? Direction. And friction would be acting along the ramp. So we put a lot of little details and little aha moments together there. So it's going to be this number divided by 60. You want the average force of friction. And by the way, the reason I'm saying average force of friction, I'm hedging my bets because I don't know necessarily that it's constant, because mu might change at different sections of the, I don't know what this ramp looks like. Maybe there's a sandpapery section and a smooth section. I don't know. You got 104? Forces measured in? It's funny, the first thing that went through my mind is, what? No, we're doing force now. Is that what the first thing when I said measured in? No? Okay, because I've had you for a while. 104 newtons. Rube Goldberg machines are great examples of energy transformations. Rube Goldberg was a cartoonist. I think he worked for the Saturday Evening Post. And what he would do on the back page of that newspaper, Tristan, is he would draw a picture of an elaborate chain reaction machine to pull to do a simple task. Maybe the task was making your toast in the morning, and there would be a lever that would pull, that would roll a bowling ball down, that would hit something, that would knock over something, that would release a cat, that would chase a bird, and the bird would fly in and knock the toast into the toaster, and the toast... chain reaction machines. And we love building these. I'm not going to show you this one, though. Put your pencil down. Cole, a bouncing ball is a great example of conservation of energy. At the top of its bounce, what type of energy does the ball have? Gravitational potential. I'll let you just say potential. What's its speed at the top of the bounce for a split second? So how much kinetic does it have? Nothing. When the ball hits the ground, what type of energy does it have? When is the ball traveling its fastest then? When it's at the bottom, because it's all kinetic. Yes? If you just let a ball bounce on its own, it loses height on each bounce. Does this violate the law of conservation of energy? No? Where's the missing energy going, Cole? Sound and heat. So here's the question. Is it possible for a ball to bounce higher than it was originally dropped? That's the question. Only if there is an outside energy source. Does that satisfy both answers, Cole, I think? Yes? That was my sneaky workaround. Mr. Duick? Yeah? What if you took a basketball, a tennis ball, and a golf ball? I have been told that if you managed to get all three to balance, and if you did that in a gym, you'd probably smash the lights of the gym. I have not been able to do it successfully myself. Haven't got it to balance. So a golfer wants to hit his drives further by increasing the kinetic energy of the golf club when it strikes the ball, because all the golf club does is pass kinetic energy onto the ball. What would have a bigger effect? Doubling the mass or doubling the speed of the club? Doubling the mass of the club or doubling the speed of the club? Why speed? Why better? Brian, that's squared. This is why all of the coaching in the past 20 years for driving distance, it's all been about club head speed. In fact, the equipment's gotten lighter. Try playing with a golf club from like 30 years ago. It feels like you're holding a rock. They're terrible. Hockey sticks, same idea. If you follow hockey, I grew up with wooden sticks. They had mass to them. Now they're lighter because it's all about the speed. It's a trade-off. There is an M in the equation, David. That is true. It's a half M, but it's V what? Oh, even if I lose a bit of M, if I can get way more mass, I'm doing great. You figured it out, Sierra? Good. Excellent. You made it? Okay. So, club head speed because of the squared. What's your homework? Number 1, in your own words. 2 is good. 3 is good. 4 is good. Yeah, 5 is good. 6 is good. I'll skip 7. 8 is good. No, I'll skip 9. I'll do 10. I'll skip 11. 12 is good. I'll skip 13. 14. I know that's a lot. I'm sorry. I'm going to... you will not have... So when do I see you next? Wednesday? Next class Wednesday, we'll be doing a lab, so you won't have new homework, and you'll get the lab done in class. So if you want to spread this out over the next while, you can. You can work on the homework, or you